Have you ever opened a datasheet or embedded C code and seen these interesting numbers that start with 0, then X, and then you have numbers and letters intermixed together? These are hexadecimal numbers, hexadecimal values. And you're wondering, why are we using these hexadecimal values in programming microcontrollers? Why not just use normal numbers? And the answer is we could use normal numbers. However, believe it or not, hexadecimal actually simplifies microcontroller programming. Hopefully by the end of this video you will understand why. We use hexadecimal a lot when we're programming registers in a microcontroller. And what are registers? Registers are something that control hardware behavior. Well, I have this example register here. This is not a realistic register, but very similar representation of it. So I have switches here. I have 8 switches, 0 through 7. And these switches, let's say each one represents a GPIO pin of a microcontroller. And each one is tied to an LED, turns LED on or off. So we can actually come here, we can say, okay, this one will be on. I want this LED to be off, and this one off, but I'm going to turn all these ones on. The number I actually wrote here is a binary number, which is 1000, then 1111. So this is a binary number, and then we use this number to program our registers. To understand hexadecimal, obviously you need to understand how binary works. So let's talk about that. Okay, to understand binary, let's first try to understand how decimal system is set up. There are a lot of similarities. So in decimal system, we've got our decimal numbers, right? We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the symbols, and we assign the number for each of these symbols. We don't have a symbol for 10 or 11, so we can make 10 or 11 from these given symbols here. So to make 10, we use 1 and then 0. That makes it 10. Well, if I asked you, what is this number? What would you say? You would probably say, this is 123. I would say, well, why is it 123? Why is it not 321? Why are we reading this ways? Well, the answer is because of the place value. We said if a number appears right here, these are ones. These will be all ones. Whatever we put there, we can put 9 there. That'll count as ones. There will be 9 ones. But over here, this is the second place to the left. And if number appears right here, then we're going to count this as tens. So if we have 2, that means we have 2 tens. If we have 7, we have 7 tens. And then over here, this is hundreds place. So if we have 1, we have 100. If we have 8, that means we have 8 hundreds. So why is this working this way? So you can think of this as powers. So if you understand powers, you'll be able to understand these different systems. They are based on some powers. So let me explain what I mean by powers. So this number here, we have decimal system. We have 10 digits, right? 10 symbols. That means we have powers of 10. So this place value right here is 10 to the power of 0. It's 0. This other one is 10 to the power of 1. The next one is 10 to the power of 2. And then if we had another one, let's say 2, that would be 10 to the power of, that would be 3. This one looks like 3, but let's fix it. 10 to the power of 4, and so forth. But let's just grab these a few numbers. What's 10 to the power of 0? So that is 1. Then 10 to the power of 1 is 10 itself. So it'll be 10. 10 to the power of 2, that's 100. Or let's just include these thousands too. So 10 to the power of 3 is actually 1,000. And these are kind of divided here. Now we're going to write our numbers here. So we have 3 over here. We have 2 over here. Or we have 1 and we have 2. When we look at this, we're like, okay, 1 threes. And this becomes kind of multiply thing. We have 1 threes, so it'll be 3. We have 10, 2 tens, that's 20, right? So I'll come here with 23. We have 100. We have 2 thousands. When we add all these numbers together, we get 2,123. So this should be no news to anybody. So everybody knows this and understands this. Let's move on to binary now. Binary works the same way. So what do we have in binary? We have 0. We have 1. 2. We have 2. No, we don't. Actually, binary doesn't have 2. Binary has 0 and 1. So with binary, you are very limited. You are limited to 2 symbols only. And when you have 2 symbols, you start talking about powers of 2. You remember the powers from the decimal? That applies here as well. Let's say I have a binary number. Here's my binary, random binary number. Powers of 2. 2 to the power of 0. 2 to the power of 1, right? 2 to the power of 2. 2 to the power of 3. Remember, this is all place value, just like in decimal. It's not very different in binary. It's same place value, but we have binary place value because we can only count up to 2. All right, what is 2 to the power of 0? It's 1. What is 2 to the power of 1? It's 2. Okay, what is 2 to the power of 2? That is 4. 2 to the power of 3, right? 2 times 2 times 2. So that is 8. Here's our binary number. We have 0, 1. How about we have 1, 2. Okay, there's one of those 2s. And nothing on this place value. We don't have any 4s. Okay, no 4. But we do have 1, 8. So we have 1, 8. No 4, but we have 2. Okay, plus 2. Nothing here. This binary number here is actually equal to 10. This might seem a little complicated, but it's going to get easier. Do not worry. Let's do a little exercise. Let's just count in binary till 15. How do we count in binary? Well, how do we count in decimal? In decimal, we count 0 through 9, right? And then when we run out of digits, we do a place value. So we say, okay, 1 here, so this becomes 10, and we keep counting 11, 12, all the way to 19, and then we have to flip the numbers. This is gonna become 20, right? Okay, binary is the same. However, you have only 2 digits, two symbols. So you count till 0, then 1. Okay, let's say 0, then 1. Then how do you do 2? Well, you can't do 2 anymore. You need another place value. So, okay, let's just add another place value. 0, 0, 0, 1. So 1 was going to turn to 0, and we're going to have this here. So this is actually 2 in binary. It looks like 10, but it is 2 in binary. Okay, let's keep counting. 3. Let's do 3. How do we do 3? We can increase this. Okay, this is 3. So let me just do, this is binary. And I'm going to do decimal here, decimal equivalent. This is 0, this is 1, this is 2, this is 3. Okay, how about 4? Can we count till 4? Well, we actually can't because we ran out of digits. So we need to have another place value. Add another place value. Now we can start counting until 4. These all kind of reach their top number. You're going to put 1 here. This is going to be binary 4. Okay, we can keep counting here now. So this would be 5. And this would be 6. This would be 7. Okay, 6 and 7. So can we count further with these many place values? Or these are actually called bits in binary. The answer is no. We kind of plateaued. We reached our top number with only 3 bits. So we need to add another bit here. So we're going to add another bit. We're going to keep counting. So, all right, now we can count till 8. So this is 8. And as you can see, it's 1, then all zeros. So you can see 1, 2 to the power of 3, that's 1, that's 8, right? So we have 1, 8, and nothing else. And over here, we have 1, 4. So this is 1, 4, 1, 2, and 1, 1. 4 plus 2 plus 1 is 7. Okay, so now let's keep counting. 9, right? Now next we're going to go do 10. So how do we do 10? We have, this is 10. 1, 8, and 1, 2. Okay, let's do 11. So this would be 11. 1, 8, 1, 2, 1, 1. That is 11. Let's do 12. 1, 8, and 1, 4 would be 12, right? So that's 12. Now next number is 13. So to do 13, we have 1, 8, 1, 4, and 1. So that is 13. Okay. 14 will be this number here. This is 14. Okay. Why? Because we have 1 8, we have 1 4. 8 plus 4, 12, plus 2, 14, and we need 1. That would be 15. So 1, 1, 1, 1. That would be 15. So we are at the max here with 4-bit. And to understand hexadecimal, actually, this is what you need. Hexadecimal, which we're going to talk about next, is base 16 framework. It's base 16 system. And you can see we just counted up to 16, starting from 0. And this will help you understand hexadecimal. Now let's talk about hexadecimal. And if you remember, we use hexadecimal to program registers. Here's a register, and we're gonna put some binary values here, and let's say we're turning on LEDs or something, some sort of hardware operation. Over here there are 16 digits here, 0 through 15. Say I'm gonna do 1 here, it'll be 1, it'll be 0, it'll be 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, 0, 1. Okay, here's our binary number. We could use a binary number like this to put into a register, right? Or person also could turn into this into decimal, but when we use decimal, we lose this bit positioning in a register, and we lose that meaning for a register. So what we want to do, we want to use binary, but using binary, as you can see, is becoming a little bit harder. So how do you take this apart from another binary number like this? It's hard to read. So that's why we have hexadecimal. And hexadecimal is base 16. Hexadecimal has all the numbers from 0 through 9. Then we have letters to represent numbers from 10 to all the way to 15. So A is our 10, B is 11, then C is 12, D is 13, then E is 14, and then we have F, 15. So why do we do it this way? We do it this way, as you can see, it goes 0 through 15. And in the previous discussion, when we were talking about binary, how many bits did it take us to be able to count till 15? If you remember. So we went from all zeros to 1, 1, 1, 1, which is 15, right? So we counted all the way from zeros to 15. That is 4-bit. What does that mean? So what we can do is we can divide this big binary number into a hexadecimal chunk. We can take 4-bit at a time, right? So I'm gonna cut it into 4 bits. So 4 here, 4 here, 4 here, 4 here. And then we can turn that into hexadecimal. So how do we do this? Okay, hexadecimal is base 16, which means it's powers of 16. 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, and 16 to the power of 3, and so forth. It keeps going on and on. So what is 16 to the power of 0? It's basically 1. 16 to the power of 1 is itself 16. 16 to the power of 2. What is that? That means 16 times 16. Okay, 16 times 16. I had to think about it a little bit. It's 256. So 256. Okay, and 16 to the power of 3. I had to pull up a calculator for this one, but that's 4096. Okay, 4096. So it keeps going on, and you can put together a really big hexadecimal number. But for us, we're working with 4 place values, so we're gonna need these 4 numbers. So all of these 4 binary numbers are 16, base 16 practically, because we divided them in that way, and we are putting it together as a hexadecimal number. So let's do that. 0x, that's how you write hexadecimal. Let's start with it actually doesn't matter which way we start. We can actually start right from here. So what is this in binary? What do you think? This number. So we have 1, 0, 1, 0. If you remember this top part, that is 8, right? That 1 is the place where 8 is. So we have 1, 8, no 4. Let me actually draw this. This will be powers of 2. So we have 8, then we have 4, then we have 2, and then we have 1. Okay, so this is our kind of metrics or little helpful guide here, help us to encode binary numbers. Okay, so let's put the binary number here, this first one. So we have 1 0 0 1 0. Okay, we have 1 8 1 2. What is this? That's 10. And what is 10 in hexadecimal? You're right, it's A. Now let's put the other one here. Well, this is all ones. This might be actually really easy. So 1 1 1 1. So we have 1 8 1 4. That's already 12. Then 2. That is 14. And then 1 15. And what is 15 in hexadecimal? It is F. Okay, next number 0 1 1 1. So we have no 8, we have 4 plus 2, 4 plus 2, and 1. And that is 7, so we can write 7 here. And the last one, we have 0, 0, 1, 1. 0, 0, 1, 1. So what does this mean? So we have 2 and then 1, which is 3. This is our hexadecimal value for this binary value. It is much easier to read. We can just say 0xAF73. This is that binary number right here. And it's easier to distinguish from other hexadecimal numbers. With binary, you have zeros and ones. After a long time looking at zeros and ones, it gets kind of confusing. Your eyes getting strained. It's hard to pick them apart. But if you have values in hexadecimal, you can take one apart from the other one because it's more sophisticated. So hexadecimal is used a lot when programming registers, as I said before. So hopefully this video cleared this up and helped you to understand what hexadecimal is and how we use hexadecimal in microcontroller programming.